Okay, now we're going to go through the exercises for section 7. The first exercises were truth tables for arguments. So what you were to do in section 2 of this exercise was to determine whether the following symbolized arguments are valid or invalid by constructing a truth table for each. In most cases, it was fairly straightforward. I will do numbers 6, 8, and 9 on the next slide and give you just the answers for the others that aren't already listed at the back of the book. So number 2 is invalid. Number 3 is valid. Number 5 is invalid. 6 is valid. 8 is invalid. And 9 is valid. So now we'll go through 6, 8, and 9 on the next slide. Use truth tables to test the 3 arguments in this exercise, number 6, 8, and 9. So let's start with number 6. And this one we have Z, and the conclusion is E or Z implies E. Okay, there's only 2 variables, so there will only be 4 lines. So let's start with Z, T, T, F, F, and then E. So T, F, T, F. As we've been talking, you go divide the number of lines in half for the first one, and then you divide it in half again until you're alternating. And we only had to do that once until we got to alternating. If it were 3, which the next one will have 3, it's 8, so it'd be 4, and then 4, and then 2, and 2, and then alternating, as we'll see. So we're back to Z. Just make sure you put the same truth values in. T, T, F, F, and same truth values again for E, T, F, T, F. So let's go back and figure out the truth value of this statement. That's an implication. And so it's, as we'll recall, only false when it's true implies false. So that makes this one true. This one's false, true, and true. And so we have this one figured out. And so now the main operator here is this horseshoe. That's the main operator. So that's one we ultimately want the truth values for. So true implies true is true. False implies false is true. True implies true is true. And false implies true is true. Okay? And so we don't have any true premises leading to a false conclusion. So this argument is valid. So let's move on to number 8 now. Okay, now I move on to number 8. And number 8 is 2 premises in the conclusion. So first premise is C if and only if D. I don't have the best writing in the world. E or not D. And the conclusion, E implies C. So we have 3 different variables, so now we know we'll have 8 lines. So as I was saying before, we'll have T, 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 F, 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 F. Divided in half for the next one, D, T, T, F, F, T, T, F, F. And now for E, we divide it again. The third one, so it alternates T, F, and so we know we're done now. F, T, F, T, F, T, F. Okay. Now we go back to D. We use the same truth values. So that was T, T, F, F, T, T, F, F. And E, we use the same truth values again. T, F, T, F, T, F, T, F. And then back to C. T, 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 F, 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 F. Okay, so we filled out the truth table. There's all the possible truth options for these three statements and variables. So let's kind of go through them. And so T, if and only if T, you guys will recall from the truth functions as we saw earlier. These are false when one or the other is different from the other. So if they're both true, it's true. If they're both false, it's false. I mean, if they're both true, it's true. If they're both false, it's true. So true and true is true. True and true is true. True and false is false. True and false is false. False and true is false. False and true is false. False and false is true and true. Okay. And so now E or not E. Now we have the negation here, so that flips these truth values. So F, F, T, T, F, F, T, T. And these are only false. This disjunction is only false when they're both false. Right? So true, false, true, 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 false, true, true. And back to the implication, these are only false when it's true implies false. So true, 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 false, true, false, and true. Okay, so remember, an argument is invalid if you have true premises and a false conclusion. So I only have a false conclusion at two different lines, at line 5 and line 7. So if we go back through this line, you see we have a true premise here, right, under here, and we have a false premise here. So that doesn't make it invalid, right? You need to have two true premises and a false conclusion. So what about this one? False. We have a true premise here, and we have true premise here. So we have two true premises leading to a false conclusion. So this one is invalid. Let's go on to number 9. Okay, so now we move on to number 9. Okay, so number 9, we have two premises and a conclusion. First premise is A, if and only if B or C. Second premise is not C or B. And the conclusion is A implies B. Okay, so again, we have 3 different variables, so that means we'll have 8 lines. T, 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 F, 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 F. So B divided in half, so B, T, T, F, F, T, T, F, F. And then C, T, F, T, F, T, F, T, F. So now we just keep plugging these same truth values in. Okay, we have C, so that's T, F, T, F, T, F, T, F. And B, T, T, F, F, T, T, F, F. And back to A, T, 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 F, 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 and B, T, T, F, F, T, T, F, F. Somewhat tedious. When we get to indirect proofs, it'll be simplified quite a bit, but you need to know the basics, that this is the surefire way of proving whether an argument is valid or not. So, all right, let's go through the conclusion first, because we know we have to have true premises and a false conclusion. So we have T implies T is true, T implies T is true, T implies F. That's the only time it's false, so false, false. So this one's true, 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 true. So we only have two instances where it's false in these 2 lines. Okay. So here we have the truth value flipped because of the negation. So F, T, F, T, F, T, F, T. So F or T is true, T or T is true, F or F is false, T or F is true, F is true, true, false, true. Okay. So we do have a true premise here and a false conclusion here. So it's possible this could be invalid. You see this one's false with the false here. So if it's going to be invalid, it will be because of this line. So let's go back, and this is the crucial line then, the fourth line. So let's look at this fourth line. F or F is false, and T or F is false. So we have a false premise here. So this, we don't have two true premises and a false conclusion. So this is therefore a valid argument. Now on to section 6.5. In here, this is where we start to get some of the skills needed to do the indirect proof. Here we are given certain logical statements, and we're given a truth value, and we're trying to determine whether the other truth value can be known or not. So for example, number 2, in section 6.5, section 1, we have Q implies N, and the result is going to be true. Now, this can be true in any number of ways. Q can be true and N can be true. Q can be false and N can be false or true. So we can't narrow down which one is going to be true or false by that alone. So it's unknown for both letters in number 2. For number 6, K and B, conjunction, and the whole conjunction is true. So as we know, a conjunction is only true when they are both true. So K and B must both be true. Number 8, S if and only if E, the whole thing is true. Well, both S and E can be false, and both S and E can be true, and make the full biconditional true. So it's unknown again for both. Number 12, H or S is true. H could be true and S could be false. H could be false and S can be true. So we can't narrow it down for that one either. So it's unknown. So 14, G and B is false. This could be either G could be true and B could be false, or G could be false and B could be true. That would make the whole thing false, or they could both be false. So again, for 14, it's unknown. For 18, not A if and only if D, and we know that D is true. And so if for this to be false, we need A to end up false. So A has to be true in order for the negation to make it false. So we do know a truth value for A in that one. And for 20, E implies not M. We know M is false, so the negation of M makes it true. And so E could either be true or false to make the whole thing true. So again, for 20, it is unknown. So now for section 6.5, section 2, we're to use indirect truth tables now to determine whether the following arguments are valid or invalid. I'll give you the answers to 2 and 3, and then I'll do 5 and 6 on the next slide. So 2 is invalid, 3 is valid, and now I'll do 5 and 6 on the next slide. I'm going to do the indirect truth method for the arguments that are in exercises for 6.5, section 2. This is numbers 5 and 6. As you'll recall, an argument, when you're doing a truth table approach to it, you put it on a single line with the double / before the conclusion. And so the indirect method, you'll recall, is that you assume that the conclusion is false. okay? And you assume as well that the premises can be made true. And so if you can make the premises true and the conclusion false, then you have an invalid argument. If you can't do that, then it's a valid argument. So let's see what happens here. So if this is going to be false, then the only way an implication is false is when you have a true implies a false. So we now know that W has to be true, and this has to be false. So the only time this whole thing is false is when we have a T implies F, because then that would make the implication false and then make the whole conclusion false. So now we have three truth values, the truth value for W, X, and Z. So we can plug in Z's truth value here, it has to be F. Plug in X's truth value, which is T. We also have W's truth value, which is T, and X again is T. So Y, if this is going to stay true, Y has to be true as well, because if this were false, then that would make this false, and true implies false would make that false. So now we have the truth value for Y, and Y is true, but we have true implies false, which makes this false, and that makes true implies false, false. So we can't make this one true. So we can't make it such that you have two true premises and a false conclusion. As a result, we can conclude that this one is valid. So let's go now to number 6. Similarly, we have an implication in the conclusion, so we're going to assume that this can be made false and that the others can be made true. Okay? So if this is going to be made false, then that would be because A would have to be true, and E would have to end up being false when we have the negation sign here. So E starts off true, but then it gets negated to make it false. So then true implies false, then becomes false. So now we have the truth value for A and E. So E is true, and A is true. B, if it's going to end up being true, B has to start off false, right? Because then it gets negated to become true. So we now have a truth value for B, which is false. So let's go back here. This has to be true, so it can't be true implies false. So this would be false over here if C were false. Then false or false would be false. And then we have true implies false, which would make this false. So C can't be false. So C has to be true, which would make this true. And true implies true makes that true. Okay, so we have C is true. And we don't have any commitments to D, so let's just make D true, which makes the conjunction here true. True implies true, so we can make that one true. So we can indeed make it such that the conclusion is false and we have 3 true premises. So if we can do that, then we know that this argument is an invalid argument. Okay, and now the last section was 6.5, section 3. Use indirect truth tables to determine whether the following groups of statements are consistent or inconsistent. Number 2 is consistent, number 3 is inconsistent, and 5 is consistent. So I'll show that one on the next slide. The reason I'm doing number 5 is because it's a little tricky to do prove consistency here. The reason it's tricky is because disjunctions have more options to make things true. So sometimes you have to kind of play with things until you figure it out. So let's go and assume, which if we're going to assume consistency, which means we can make them all true. All the statements. If we can't make them all true, then we know they're not consistent. So it's different from an indirect truth for valid arguments, because there you assume it's not valid, and you have the false conclusion and the true premises. But for proving consistency of statements, you assume they're all true. Well, as we know, for disjunctions, right, a disjunction, it's true in all cases except for when they're both false. So we can begin with J is true, for instance, okay? And P can either be false or true. So let's just make, for the sake of argument, make P false, and the negation sign makes it true. Okay, so T or T makes that true. So we're taking J is true and P is false. So let's hear that J is true, the negation sign makes it false. So in order to keep that true, we have to make the X true, otherwise false or false would be false. So now we have a truth value for X, it's true, negated makes it false. And so T has to be true if that's going to work, right? If we had false or false, that would make it false. So now we have a truth value for T is true, gets negated as false. And so S has to be true again. And so S is true and gets negated as false. But we had assumed F was false over here in order to make it true. And false or false would make this false. So okay, that way it didn't work. Well, let's make F true then, or P true, and then it gets negated and makes it false. Still true or false is true, and so we can go back here and make T true, and that'll make that true. If there's anything else we have to change, we just change P truth value, and that doesn't affect anything else. So we are able to make all the premises true, or all, not the premises, all the statements true, and so therefore this is consistent. So let me go back over that to kind of show you what I did in case it was a little too fast. I started off with T for J, and I assumed, just for the sake of argument, that P was false. And when I worked it all out, when I got back here and I plugged in the false P, that made the whole thing here false, which isn't something that worked, so I needed P to be true instead of false. So I went back to the original and made P true instead, right? So P is true, and it gets negated, it becomes false. True or false is still true. And by changing P, I didn't change J, I only changed P, and the P was in any of the other statements, and I was able to make all the other statements true. So I was able to make all the statements true. So therefore, this is consistent. And the last section, section 6.6, we are to interpret the following symbolized arguments in light of the 8 argument forms presented in this section. That we've already talked about those argument forms in the video for section 7. And if it doesn't fit into any of the valid argument forms, then it's invalid. So number 3, for instance, does not fit into any of the valid argument forms. It looks like a disjunctive syllogism, A or not Z, but it would have to be A or not Z in order for it to be a legitimate disjunctive syllogism. So it's not in accordance with any of those valid argument forms, so it is invalid. Number 5 follows modus ponens, so it is a valid argument. That's what the MP is for modus ponens. Number 9 does follow the hypothetical syllogism. It's not in the order that we might have seen it ordinarily, but as we will see in proofs, it doesn't really matter what order they're in, as long as they're somewhere in the statement. So you can see we have G implies not B, and not B implies not L, so we can conclude G implies not L. So that is hypothetical syllogism, and it is valid. And number 11 doesn't fit in with any of the rules. It might look like it's constructive dilemma or destructive dilemma, but it's not. If we look at the rule, you'll see it doesn't follow that rule, so therefore it's invalid. But number 15 does follow the rule for destructive dilemma, and so it is valid. So as we'll see as we move into the next and final section for this course, when we do logical proofs, as long as we're following these rules, we know we're going
correct all the way through. So in some ways, doing logic, you know you're getting it right each step of the way, as long as you consistently plug in the rules correctly. So now it's time to move on to the next and final section of the course.